Example 1512. The box shown in the figure has a mass m and it's traveling down the smooth circular ramp, keyword circular, such that when it is at an angle theta, it has a speed v. So at theta, it has some speed v. Determine its angular momentum. So what's its angular momentum? Well, we can just jump straight to our scalar formula in this case because we're talking about a tangential velocity, right? If this is on a circular path, then it has a tangential velocity which would be perpendicular to that radius arm, and we could jump straight to RMV and give it a direction. Throw a vector sign on it. Okay, that's literally the answer. What about the rate of increase in its speed? So let's also find dv dt. Well, for this, I'm going to sum the moments about point O and use the definition we just came up with that all the moments acting upon O is going to change the angular momentum with respect to time. And in this case, our moment, let's draw a free body diagram. If this is at some angle theta from O, if that's theta, then we can call this theta, which is an extension of the object's mass times the acceleration due to gravity. That's our tangential direction, and this is our normal direction. And we can say that this length right here is the radius. If this is our angle theta, I'm going to extend the weight upwards and make a right triangle right there. Okay, if that's r and that is theta, SOHCAHTOA tells me that this is r sine theta. Alright, we do have a normal force acting on this. I'm going to draw it because it is a free body diagram. But if you remember from statics, if a force acts through the point we're talking about, O, then it provides no moment. So we're not going to use it. The thing that's giving us a moment is mass times the acceleration due to gravity, and it's acting this distance away, r sine theta. Okay, so let's follow this through. The moment, or the summation of the moments, there's only one, would be the weight mg, and the lever arm distance in this case is r sine theta. Alright, what about the time rate of change of angular momentum? Let's just write that time rate of change of angular momentum. Radius times mass times velocity. The mass and radius are constant, so the derivative only goes to this term. So we can say Rm dv dt excuse me, is equal to mg r sine theta. I see a common term, let's get rid of it. I see another common term, let's get rid of it. And we're looking for the speed, we're almost there, right? dv dt at that point, or at any theta, is going to just be equal to g sine theta. Alright, we can do the same thing by applying our equations of motion that we would get from summing the forces. And this might be an easier method, just showing you another tool in the toolbox. So if I summed the forces in the tangential direction, which was going like that, and let's call that positive, we have a I'm going to keep it as this being positive, or just because of the way I have the angle theta for right now. Otherwise this would become more complex and it's really just a two-liner. So if I sum the forces, and that's equal to mass times the acceleration, I get mg sine theta, just the component of its weight, right there, mg sine theta. If I'm going to do another free body diagram, we would have mg down, this would be our theta, and mg sine theta would be the one in the tangential direction. That's going to equal to our mass times the acceleration in the tangential direction. Well, the acceleration is dv dt, right? And we can go ahead and solve for this again. dv dt is equal to g sine theta. That was a little more straightforward than this method. Just another tool in your toolbox.